For over a century, we've been told airplanes fly because air moves faster over the curved top of the wing, creating low pressure that lifts it into the sky. It's neat, it's simple, it's what every flight school and textbook says. But that story isn't the full truth. In fact, it's only half right. Engineers, pilots, and scientists still debate what really keeps a plane airborne. And the answer? It's far more fascinating, and much more important than most people realize. Because once you understand how lift truly works, you'll never look at a wing or a takeoff the same way again. If you've ever taken an aviation basics course or flipped through an old pilot training manual, you've probably seen this famous diagram. A wing with a curved top and a flat bottom. The story goes that the air flowing over the curved top has to travel farther than the air moving underneath, so it moves faster. Faster air means lower pressure, and that lower pressure sucks the wing upwards. That's Bernoulli's Principle. Pressure decreases as velocity increases. It's simple, it's tidy, and it's easy to visualize. The problem? Nature doesn't like simple. Air doesn't know it's supposed to meet up at the back of the wing. There's no cosmic rule forcing the air molecules to reunite on time. In fact, experiments show the air above the wing reaches the trailing edge before the air below. So, if that's true, then the common classroom diagram is wrong, or at least incomplete. The real story of lift involves something deeper, the way wings control the motion and momentum of the air itself. Let's be clear, Bernoulli's principle is absolutely real. It's the misunderstanding of how it applies that's the issue. Textbooks often show a picture-perfect airfoil, curved on top, flat underneath, with airspeed differences neatly explained by the longer path argument. But in reality, aircraft wings come in thousands of shapes, sometimes nearly flat, others symmetrical, and many that can even work upside down. Aerobatic planes, for example, fly inverted all the time. Their wings are symmetrical, so both sides are identical, meaning the longer path story can't possibly explain why they still produce lift. Even more striking, simple flat plates, literally thin sheets of metal angled slightly upwards, can create lift. So can fighter jets flying with negative camber. And then there's the myth of suction. Many think lift comes from the air being sucked up, but wings push air down just as much as they pull upward. That downward motion is critical, and it leads us straight to another law of physics, one that explains what Bernoulli alone can't. More than 300 years ago, Sir Isaac Newton wrote something that would eventually help explain flight itself. For every action, there's an equal and opposite reaction. It's one of those simple lines that hides an entire universe of physics. When a wing cuts through the air, it pushes that air downwards. That's the action. The equal and opposite reaction is the air pushing the wing upwards. That's lift in its purest, most physical form. You can actually see this principle every time a plane takes off. Watch closely as an aircraft races down the runway. Behind it, trees sway, dust kicks up, and the air seems to ripple. What's happening is the air being deflected downward by the wings. In slow motion wind tunnel footage, you can see a smooth sheet of air flowing off the trailing edge, something called downwash. It's invisible in normal light, but that downward stream is the unmistakable fingerprint of lift. But here's where it gets interesting. Newton's explanation is solid, but it's not the whole story. If it were about pushing air down, wings could be flat plates. In reality, air doesn't simply bounce off the wing like ping pong balls hitting a wall. It bends, curves, and follows the contour of the wing. This happens because air is a fluid, not a collection of independent particles. It clings to the surface thanks to viscosity, the same property that lets water stick to your hand for a moment before dripping away. This stickiness of air is what allows the flow to wrap smoothly around the wing, changing direction without breaking apart. The wing's angle of attack, the tilt of the wing relative to the oncoming air, and its shape together guide that air like a ramp, sending it downward in a controlled arc. And here's the beautiful part. That same deflection, the one Newton described, also speeds up the air moving over the top of the wing. As it accelerates, the pressure above the wing drops, exactly what Bernoulli's principle predicts. So, while one explanation talks about forces and the other about pressure, they're really describing the same event from different perspectives. One is about what the air does to the wing, the other is about what the air feels as it moves around it. Put them together and you start seeing the full picture, the delicate, invisible dance that keeps an airplane in the sky. So, who's right, Bernoulli or Newton? The truth is, both are. They're not rivals in some grand scientific debate. They're simply looking at the same miracle from two different angles. When a wing slices through the air, several things happen at once. Air speeds up over the top, dropping in pressure. That's Bernoulli's side of the story. At the same time, the wing pushes air downward, creating an upward reaction. That's Newton's contribution. And in between, there's a whole world of invisible forces at work: viscosity, circulation, and boundary layers, all combining to keep a plane suspended in the sky. One of the key players is something called circulation. It's a swirling motion of air that wraps around the wing like an invisible vortex. You can't see it, but in wind tunnels, scientists can trace it using smoke streams. The circulation interacts with the wing's forward motion to create a continuous pressure difference between the upper and lower surfaces. The faster the circulation, the greater the lift. It's a subtle dance between motion and pressure, each feeding into the other to maintain balance. Then there's the unsung hero of flight, the boundary layer. This is a thin sheet of air, sometimes just a few millimeters thick, that clings tightly to the wing's surface. It may seem insignificant, but it decides everything. How air flows, when it separates, and when the wing stalls. If that layer stays smooth and attached, lift remains strong. If it breaks away, the wing loses its grip on the air and the lift collapses almost immediately. That's why modern wing design relies heavily on computational fluid dynamics, or CFD. Engineers use millions of simulations to track airflow molecule by molecule, predicting exactly how the air will behave under different speeds, temperatures, and angles. It's no longer about guessing or chalkboard equations, it's about controlling the invisible, turning chaos into balance. Let's see how all this theory looks in the real world. Start with STOL aircraft, or short takeoff and landing planes, the bush pilot's best friends. These are the rugged little workhorses that can take off from places most planes would never dare. Jungle clearings, icy mountain ridges, even riverbanks covered in gravel. Aircraft like the Pilatus Porter or the de Havilland Twin Otter are built to do the impossible. They can leave the ground in under 200 feet, sometimes before a car even hits highway speed. Their wings are like living machines. Massive flaps extend downwards, sometimes nearly 40 degrees, changing the entire shape of the airfoil in an instant. At the front, small panels called slats slide forward, helping the air hug the surface of the wing instead of breaking away. That's how they generate huge amounts of lift at incredibly low speeds. Not by brute force, but by controlling the air's behavior. Watch them take off and you can literally see the air being thrown downward behind them. A perfect example of Newton's third law in action. Yet the pressure difference described by Bernoulli is still at play, keeping the airflow smooth and steady. Both principles are working together, perfectly balanced. Then there's inverted flight, the ultimate mythbuster. Aerobatic planes like the Extra 300 or Pitt Special roll and twist through the air as if gravity doesn't apply to them. Their wings are symmetrical, the same on top and bottom, so there's no longer path creating lift. Instead, the pilot just tilts the nose downward, changing the angle of attack. That small movement makes the airflow downward beneath the plane, and the equal and opposite reaction pushes it upwards, even whilst it's upside down. Watch high-speed footage of these flights and you'll see the same downwash pattern forming. Still, the pressure difference matters. Even a tiny change in how the air clings to the wing can mean the difference between a clean roll and a stalled one. And finally, look at the Airbus A380, one of the greatest feats of engineering ever built. Each wing stretches almost 80 meters across, wider than a basketball court as long, and each carries over 30,000 gallons of fuel. Inside them are sensors, hydraulic lines, and tiny mechanisms that allow the wings to flex and twist while flying. The flaps extend in stages. The ailerons make hundreds of adjustments per second, and the wingtips shift shape mid-flight to smooth out turbulence. Every inch of it was tested and refined through supercomputer simulations using advanced fluid dynamics, predicting how air would behave molecule by molecule. The result is a 560-ton aircraft that rises from the runway as gracefully as a bird. Stand at the edge of an airport fence and you'll see the air swirling behind it in two massive spirals, a visible trace of the invisible forces keeping it aloft. In that moment, the theories of Bernoulli, Newton, and Kutta-Joukowski stop being equations on a whiteboard and become something real, alive, and moving. 100 years ago, humanity barely understood what made flight possible. Today, we've learned to shape it, to sculpt the air itself. Here's where lift gets truly beautiful and mind-bending. As air moves over and under a wing, it doesn't just flow in straight lines, it swirls. This swirling pattern is called circulation, and it's what gives rise to the famous Kutta-Joukowski theorem, the equation that ties lift directly to the amount of circulation and airspeed. In simple terms, the more circulation, the more lift. When a pilot pulls back on the yoke, increasing the angle of attack, they increase that circulation. The wing pushes more air downward, generating more upward force, but every bit of lift has a cost: drag. Push the angle too far, and the airflow can't stay attached. The boundary layer breaks away and the wing stalls. It's the same reason you feel turbulence as sudden drops. The airflow becomes chaotic and lift disappears for a fraction of a second. It's an incredible balancing act. Every takeoff, every climb, every landing is a constant tug of war between smooth flow and turbulent separation. Pilots manage this dance instinctively, feeling the invisible forces of pressure and motion through their fingertips. So what really keeps a plane in the air? It's not just Bernoulli's smooth curves or Newton's simple reactions. It's both, and everything in between. It's how wings shape and steer air, how momentum becomes pressure, and how humans learn to bend the laws of physics to their will. Next time you're by the window, take a second to watch the wing. The flex, the tilt, the air streaming past. That's physics in motion. It's not just metal cutting through the sky. It's human ingenuity mastering something nature never meant us to do. And if that still amazes you, good, because the story of flight isn't over. There's always another question, another mystery waiting above the clouds. If you enjoyed this look into the hidden science behind flight, give this video a like and subscribe for more stories from the skies.